record. Okay, now it should be recording. So this is our final project for CPE 185. I'm Alex Zemchik.
I'm Deepak Sharma.
And the first thing we're going to talk about is our logic of our project. So we decided for our final project to create a fully functioning alarm clock with we used a STM32 Nucleo as our microcontroller. That was one of the requirements. We decided to go with the Nucleo because we felt we were more comfortable with it, and we had already done some projects with it. And our design, we had planned on using 4 7-segment displays, 2 push buttons, and a buzzer. However, due to the coronavirus, COVID-19, we were not able to purchase the necessary equipment for us. We were not able to purchase transistors to be able to use 4 7-segment displays at once. So instead, we ended up using 2 7-segment displays, and we displayed both the minutes and the hours on those 2 7-segment displays. And as well as the buzzer, we were not able to use a buzzer because it as well needed a transistor to work, but instead we used an LED to represent our buzzer. And the kind of 7-segment display we used was a common cathode 7-segment display, which basically means it has a common ground. So the 7-segment displays we had a common ground. We had 2 push buttons, one for snoozing the buzzer and one for turning it off completely. And when I say buzzer, I'm referring to our LED. And basically, we had a button which would snooze the alarm. So it would turn off for a set amount of time, and then it would turn back on until we press the off button, which completely turned off the LED. And we had to display our minutes and hours with the counter. Basically, we had to make sure that our minutes and our hours were displayed correctly and in order. And the minutes, they only range from 1 to 59, so we had to set the limits for our displays to only go to 59 for the minutes and then only up to 12 for the hours, because there's only 12 hours in a day. And we also had to use a finite state machine to switch from different states. So we had a state in which we displayed our minutes, we had a state in which we displayed our hours, and then we also had the state in which our buzzer was turned on and off, which aka is the LED. And then now Deepak will talk about the test cases.
The test cases we presented were, we tested the snooze option to see if the alarm in fact turns back on after a certain amount of time. We chose a 5-second snooze time, and after the 5 seconds, the LED lit up again. We also tested the off button to make sure it fully turns off the alarm until the set time is once again reached. We pushed the second push button and turned off the LED until the set time was reached again. We also tested to see if the buzzer goes off when the alarm hits the set time and if it turns off with the snooze and or off button. We used a scale of 1/6 to display the minutes and hours, so 1 second would equal 1 minute in real life. We also tested to make sure the hours and minutes change at the same rate as a real life clock would. We tested the accuracy by using the stopwatches on our phone compared to the alarm clock we created.
All right, and then the pinout. So basically right here we have a picture of the STM microcontroller and the pinout of it. And as you may see, there are pins on both the left and right side, and the ones we used for one of the 7-segment displays was PA0 through PA6, because there's 7 segments, you need 7 pins for it. And as you can see, PA2 is way up here, and it's actually A7 on the board. Therefore, when we were wiring our 7-segment display, we had to make sure that our wires corresponded correctly to the pins on the board. So we couldn't just rely on the software and what is said on the Cube software. We had to look up this pinout and make sure we wired everything correctly, as well as the PB. If you look on this left side, you could see how the PB is way more random, how it has like PB0, PB7, PB6, PB1. So we had to be especially careful with the PB pins because of the complete randomness of the pins. And yeah, that is our final project. All right, let's stop recording if I can do that. Okay, stop.